Okay. Hey, we're going to take a look at the Biot Savart Law now. So this is a way of calculating the magnetic field strength to find the magnetic field made by charge flowing down a wire. So made by a magnetic electric current making a magnetic field. So take a look at this. For my first example here with Biot Savart Law, let's say that we have a long straight wire, right? How long? Well, we're going to make it infinitely long in a minute, in a few minutes here. But for starters, just imagine it's a really long wire. So we have a long straight wire. And to make a magnetic field, I have to have moving charges. So the charge, so say we have a long straight wire. Not carrying a charge, with a current I flowing through it. And what we want to do is we want to find the magnetic field strength. Okay, so we want to find B. Okay, at a position. Okay, that's some distance away. Okay, what do we want to call that distance? I don't know. Let's say that distance is at a position. We'll say it's A, distance away. Yeah, that was fine. That was fine. I did that. Okay, so here's what that picture looks like. Here I have this long straight wire, right? And we're going to run a current down the wire. Okay, and that current that's flowing along the wire, we're calling that I. Okay. And what I want to do is I want to find the magnetic field at a location, say, right here, okay? Now at this point, we say, hey, right hand rule. I want to grab the wire with my right hand so my thumb points along the current. So I'm going to do this like this to the right, yeah? Grab the wire, my fingers would curl around like this. That means above the wire, the field lines are coming out of the board. So I'm going to draw a dot. Okay, so like right there, right? Hey, I want to know right there, how big is magnetic field strength at that point? Okay, where is that point? It's this distance, I'm just calling little a away from the wire. Okay? Make a little right angle there. Right? Okay, so it's like that's the distance away. All right, there we go, that's the plan. So we need to figure out an equation, a formula for this, for figuring this out. So what we're going to do now is I'm going to logic through with you the Biot Savart Law. Okay? So here's the deal. This field here, it's being made by current flowing in the wire, right? Is it being made by current flowing in the wire right here? Sure. What about some current flowing here? Well, yeah, that'll contribute some field. What about the current here? And the current here, and the current here, and the charge here, and charges back here, and here, and here, and here. They're all contributing and making some field there. And I'm going to add it all up to get the total field coming out there, yeah? Okay. So you say, so what I'm going to do is, to figure this out, I need to figure out the field made by current in just a little bit of the wire. And I'll add up the contribution to the field made by each little bit of the wire that has the current flowing through it. Make sense? So for my example to do, I'm not going to do the special case that's just straight perpendicular. I'm going to pick just like a random spot off to the side. Okay? So I'm going to think about a little length of the wire here. Okay? So like right here. This little bit of the wire here. Okay? This is not the full length of the wire. This is like a little DL of the wire. Okay, a little differential length of the wire, right there. Okay, I'm going to add up the contributions by each little infinitesimal little bit of the wire. Okay, so that's the plan. Does it make sense to you that the more wire I have, with current going through it, the more field I would have, right? So what I'm going to do is, like I said, I'm going to find the little bit of field, not the B. I'm going to start by figuring out just the little bit of field strength made by the current flowing through this little length of wire. In other words, I'm going to write my formula not for B, but for dB. The little bit of field here that's made by this little bit of wire here. All right? Believe it or not, this is the way that the Biot Savart Law is written. It's written in terms of dB that's made by this little dl bit of the wire. All right, so we're trying to write an equation for dB in terms of dl. You say, okay, so what else is going to affect, do you think, how strong the field is there? And you say, okay, well, certainly I know that moving charge makes the field. The more charge I have flowing down that wire, the more field I should have. So current should be in my formula. You say, sure, okay. What else do you think ought to affect how much field I make here? And I hope you would say, well, doesn't how far away I am have an effect? So let's invent a little arrow here. You might say, I want to invent a little arrow, we'll use pink, from here, to that little length of wire here, right? To here, yeah? Okay, we'll call that distance there. We'll call that distance r, right? And you say, certainly as r gets bigger, the field there should get smaller. So what do you think? Is it just going to be an inversely proportional to r? What do you think? The field made by this little bit right here. As I go farther out, that field should get weaker and weaker, right? Well, if you think back to what we've done before with gravitational fields and electric fields, as an influence of something has to spread out in 3 dimensions, right? Over a bigger and bigger volume, right? As it spreads out, it gets weaker, right? Okay, that influence. So, for example, an electric field is the easiest one to talk about because we've done this a bunch. Imagine I have a little positive charge, right? And it makes an electric field around stuff like so. Junk, 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 right? You say, we talked before about using Gauss's law and thinking about it, but you say, hey, look, if this is a field radiating out, if I drew a closed surface, right? Remember that the field strength, right? Why am I doing it in blue? We know that my electric field strength, we said it ends up being equal to the number of field lines per area. In other words, how densely packed the field lines are. The more field lines I have per square meter, the stronger the field. In fact, it comes out to be exactly equal to the number of field lines over the area, right? If I rearrange this, I would get that flux. It says E times A, but what if E isn't uniform over the area? Well, let's split it into a bunch of little pieces, right? And so it'd be E dot dA, right? And the dot parts, we care about the angle between E and the area, right? You say, okay, that's great, and I add it up over that surface, and that's how I calculate my flux. We said, now it turns out that if I make my surface a closed surface, a bubble that encloses charge, right? Maybe there's a little bubble with a radius r, right? If I do that, then I end up getting a field. I make a closed surface that's equal to the charge in over epsilon naught. You say, hey, that's Gauss's law for electric fields. I'm going to come back to this equation in a minute for this magnetic thing, so hang in there. I did this for a reason. And so you say, so the point is, though, when I do this, you remember that when I do that closed surface for this bubble, we say, well, we came up with this realization that for a point charge or spherical geometry, that as I go further out, if I were to double the r, right, you say it's the same amount of flux going through, but the area, when I think about my field strength being flux per area, this is really what I'm looking at for right now. Flux per area, you say, hey, if I make this twice as far out, I have the same amount of flux, same number of field lines. Every field line that went out this bubble goes out this bubble, right? But the area now is bigger, and so the field strength's weaker. Hey, the area of a sphere, anything that spreads out evenly in 3D, right? The area of a sphere then, that would be 4 pi r squared. And so, the surface area of a sphere. And so you say, so our electric field strength is proportional to 1 over 4 pi r squared. It's an inverse square relationship, but specifically, it's 1 over 4 pi r squared, right? And that's why we wrote Coulomb's law, right? We said that electric force was KQQ over r squared, but that K, remember? And if I rearrange this and talk about the force per charge, now I'm talking about the E field strength, KQ over r squared. We said, but wait, this is a charge making the field. We said, but wait, that K, that's really 1 over what? 4 pi epsilon naught, right? You know what I'm saying? This is the K there. And so you see it's 4 pi r squared. We just lumped the 4 pi with that epsilon naught into that constant. But it's really 1 over 4 pi r squared, Okay, it's because this geometry is spreading out in 3D. So you say, so get back to the magnetic field. You say, yeah, this little bit of current here, and this little length of wire here, is going to make a field that spreads out in 3D. So this really ought to be proportional to 1 over 4 pi r squared. So in my formula there goes, this ought to be over 4 pi r squared, right? Okay, for now I'm putting like a is proportional to sign here, right? Okay, anything else that should affect how strong the field is here? And you say, well, yeah, there is something else. The other thing about it is, and this is awkward, but B field's a vector. It needs a direction, right? What's a vector in here? Well, that DL's a vector, but that's not the way the B field goes. The B field's going out of the page, right? You're like, I remember the B field has to be perpendicular to the charges flowing, right? The direction the current goes, right? It always goes around the wire, making a right angle to the current, yeah? Right? So it's got to be perpendicular to DL, right? But it needs to also end up pointing straight out of the surface in this case. And by the way, on the other side of the wire down here, it would end up going straight in, right? It's got to be perpendicular to the plane here. Well, you say, well, that sounds like I'm going to do a cross product, right? Because I need a cross product to get a new vector out, right? A dot product wouldn't give me a vector. That's a scalar product. So you say, so I need another vector that's in this plane. So what we're going to do is we're going to take, oh, let's just take this R guy and make that R guy a vector, right? And so then you're saying I could do this. Droop, droop. Now it's a vector and perpendicular to DL and R, right? Maybe I do a cross product of DL crossed with R, droop, droop, right? And you say, look, R cross F, R cross L, DL cross R. Yeah, DL crossed into R would be out of the page. Hey, that works. And if I was down here, right? Down here, if I was like a distance away on the other side, right? And I was right here, my B field had better be going into the page, right? Right hand rule, right? Grab the wire with the right hand, field lines go in the page below, out of the page above. And if I did my little R vector down there, right? And I did R, because I'm doing DL cross R. So if I did DL cross R, that gets me into the page, see? L cross R, in the page down here, up here, L cross R gets me out of the page, yeah? Fingers along the first vector, DL, curl, go on the second vector. DL on the first vector, fingers along the first vector, DL, curl to go on the other one. So that works. That works, all right? But then there's a tiny little problem that we just introduced to our formula. Okay, fine, it's a big problem. When we introduce this new vector, and that's, what's going to happen with this R and this R? When we do the calculation, it's going to be like DL times R times the sine of the angle between them, right? Okay? And you say, but this is supposed to be proportional to 1 over 4 pi R squared. And I just put another R on top. That's going to like screw up my quantity, isn't it? I introduced this cross R just to get a direction, okay? And also to get this sine theta factor, which I'm going to talk about in a second. He's saying, but most of this is just to get a direction, that the force is straight out of the page, right? Okay, I didn't want to change the strength of the force. So here's the trick we do. Instead of inventing a vector R that goes from here to here, we invent this guy. All right, we're going to invent, I'm running out of colors here. Use this plum one. We're going to introduce a little vector that goes like this, that way. But this guy, it just has a length of 1. It's a little vector that has a length of 1, so that doesn't change the size of things. It's not the same as this full length, okay? It's just a unit vector in that direction. It's a vector with a length of 1 unit. When I have a unit vector, like remember we do I, J, K notation for vectors? These are unit vectors, I, J, and K. We multiply values by to get the vector in that direction, in the X, Y, or Z axis. I put little circumflex symbols over them to indicate it's a unit vector. The little hats, okay, sometimes they're called. This is an R hat vector. Okay, so this R, full R, that's this distance, and this is not a vector. But this is going to be r hat. And that has a length of 1. Okay? And this is almost the Biot Savart Law. Okay? One more comment. You know that cross product means there's a sine theta hiding in there. Okay? Where theta is the angle between path along the current, along the wire, DL, crossed with that r vector, the vector towards the direction that we're, unit vector in the direction towards where we're finding the B field. This here, that would be theta. Okay, that's our theta right there. Okay, so there is a sine theta. So what that means is, if I'm this distance r away, the field strength that this current makes here, this little bit of current, the field that it makes, and this little bit of length of wire, will be different strengths. You say, well, that kind of makes sense. If I'm here, that angle would go to 0, and the sine of 0 is 0. I get no field. But as I go out here, I get sine theta gets bigger, bigger, bigger. It gets maximum when I'm straight above that point. So actually, the little bit of charge here will make a stronger field there than a little bit of charge over here. It's also closer, but the point is that the angle matters. Okay, so I do want that sine theta. Okay, hey, I want to take this is proportional to and make it an equal sign. But there's one more thing that'll affect how strong the field is here. Okay, I'm going to lump it in there. When I went to find my force, electric force, I'm going to back up a step, with E field strength, with Coulomb's law, right? And we said, hey, it depends on how big this charge is and how far away I am. But there's one more thing hiding here. That's this epsilon naught guy. Remember that epsilon naught? That epsilon naught guy was called the electrical permittivity. It's easier to see its meaning in this equation, in Gauss's law. I told you I was going to come back and use this. If I cover up this part, I know that if I've got charge, it makes flux, right? It makes electric flux, number of field lines, right? You say, well, how many field lines does a certain amount of charge make? There's some sort of I need some sort of a factor to compare to each other. Well, that's what this epsilon naught is. It's a scaling factor. It tells me how much flux I can make for how much charge, right? Yeah? What happens if epsilon naught is bigger? Then this certain amount of charge makes less flux, right? Divide by a bigger number, yeah? The epsilon value in our universe for empty space is called the vacuum permittivity, right? An empty space in vacuum. And that has a set value. Remember what that was? No, you don't need to because it's on the formula sheet, but it's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. But anyway, the point is that's a set value. But what if I want to push my E field lines through some different material instead of vacuum? Then that epsilon value would change, right? The permittivity would change for different materials. We show that by multiplying our epsilon naught by this kappa guy, the dielectric constant. Remember? So if I'm trying to push field lines through like the dielectric in a capacitor, for example, I'll make a weaker field overall because of that, right? That kappa alters, you got it, right? Because those ions inside the dipoles inside that insulator and the dielectric, they align themselves to make their own field that fights against the E field, the external E field. And they reduce then the total E field between the plates. Okay, if you don't have it hooked up to a battery, just kidding. You can put it in dielectric. Anyway, talked about that before. Hey, point is, we need a similar quantity, something kind of like epsilon naught, to serve that job here for magnetic fields, right? That constant we're going to put in there to make this an equal sign. Instead of calling it epsilon naught, right, that Greek letter lowercase epsilon, we're going to use a lowercase Greek letter mu. So we're going to use the symbol mu naught. And now that's an equal sign. Okay, what's that mu naught? Well, you know how the epsilon naught guy was called the electrical permittivity? And it's a measure of how difficult it is to push the electric field lines through. If it's naught, it's empty space. If it's not naught, if kappa times it, then that's through whatever material. How difficult it is. The bigger this value here, kappa epsilon naught, gets, the harder it is, the less field lines you get. This guy, on the other hand, what happens the bigger mu naught gets? Well, the bigger the field would get. It's the opposite. Instead of being how difficult it is to push field lines through, mu naught is how easy it is. It's like just looking at it from a different point of view. It's on the numerator here, it's on top. So this is going to be, it's called the magnetic, and not permittivity, because the bigger permittivity, the less field you get. It's got to be something different. The bigger this is, the more you get. So we call it the permeability. Okay? If something's permeable, that means that like stuff can go through it, right? Yeah? You know that word, right? Permeable membrane, semi-permeable, you talk about that, right? And so the more permeable, the more you get, right? The more flux you get flowing through it, right? Bigger this, bigger this. Permittivity is like, well, it's a measure of how difficult it is. I don't know how you're going to mentally think about that. But it just made me realize the bigger epsilon naught is, it's like, this is not a good name. But anyway, but like the bigger this is, the less you get. So it's kind of just saying it's coming from the other way around. But that's it. That's the value for magnetism. Now, you say, what if I had a different material? What if I wasn't trying to push it through empty space, right? Oh, by the way, this permeability, oh, check this out. You're going to like this. You know what the value is for empty space? Mu naught? For empty space, mu naught is 4 pi times 10 to the negative 7. Why do you like that? 4 pi, oh, it simplifies the equation. Isn't that cool? That's because they invented the units on these things are based around this. And so we made like the Tesla, right? It's like what, Tesla meters per amp, I think? I want to say that's the units for this mu naught. I should double check that. I'm pretty sure it's Tesla meters per amp. They when they invented the Tesla, it was based around this idea, and it makes the equation simpler. Isn't that neat? They defined the unit to make this equation nice. So anyways, that's it. And then 10 to the minus 7 is there because they want to have enough that you can see the visual effect visually. We'll talk more about that later. So that's it. Okay, that is the Biot Savart law. You're like, wait a minute, don't you have to integrate it? What, you're leaving it in terms of a differential? Yeah. This is the Biot Savart law. Sometimes, instead of calling it the length, you know how if I've got a wire, this is for a long straight wire, it makes sense to call this a little bit of length. Sometimes I'm dealing with wire that's bent in curves. You're going to see why in a little bit. Then it makes sense, usually I do like ds for arc length instead. But anyway, but that's the formula. And this is how it looks on the AP formula sheet. In the old days, the formula sheet, they just had r, and then they made this r cubed to kind of cancel out that effect. See what I'm saying? Kind of balance that out. But that was weird because then it kind of hides, why is there a 4 pi r cubed in the bottom? You had to explain, it's because we had to do this cross product up here. And it's better to just invent a new little unit vector. And this is better for solving and working with it. It's better to think about crossing with the unit vector. Okay, it really is better. You'll see. Okay, so that's the Biot Savart law. And that now I've kind of broken it down and talked about where all the bits come from and what they mean, right? So now we're going to use it. Okay, so here we go. So Biot Savart law, we're now going to use it to solve this. Okay, I need some space. All right, here we go. Okay, so I'm going to go to this one. Now, I've got this wire that has some length, right? Maybe it goes from here to here or whatever. I'm actually going to solve, I'm going to solve in general for a wire, a long straight wire of whatever length. And I'll show you how we'll derive that. And then we'll talk about the special case of what if the wire is infinite. And that'll give us that formula that I showed you before. In passing real quick, just cheated and told you the formula for a long straight wire was, we're not going to say it again now, we're going to actually derive it. Okay, so here we go. We want to use Biot Savart law to find the B field strength here. Here we go. You say, all right, this is going to be easy-ish. Okay, it's not. This is one of the longer derivations that I do. Okay, but hang on, hang in there with me. So, I know, it's already been a long time. Here we go, dV. If I did this, I'm going to go ahead and I want to set up this equation, and then I'm going to integrate both sides, okay, is what I would do. So I'll take it, I'm going to integrate both sides. Running through here, you say, well, first of all, well, yeah, let's just write it like that. Sure. I'm going to add up until I get the total B field, and I'm going to add up until I get whatever this comes out to be, all right? For the total length of a wire, from wherever to wherever, okay, is what I'm doing. Okay, now let's take our constants out, okay? Let's take the constants out. Okay, mu naught, that's a universal constant, okay? 4 pi, hey, I, the current in the wire, that's a constant, right? I'm going to stop color coding if that's okay with you. Thanks. Now what's left? I'm not going to take an integral. dl, that's our variable as we're going along the wire. Our hat, there's this sine theta in there, right? Yeah? And so you're like, well, that's kind of awkward. All right. Now, our hat has a value of 1, right? So that's just 1. It's just going to go away, but I have this sine theta hanging around, okay, from the cross product. Down here, I got that r squared. That r is going to be different as I go along the wire. That length of r is changing all the time. So I see that in the integral here, annoyingly, 1, 2, 3 variables. And you're like, yuck. If I want to take an integral, I have to get it all in terms of one variable, right? Sorry, when I integrate this, I'm just going to get b, right, on this side. So b will be equal to this. So you say, to find b, I got to resolve this. 3 variables, I got to get in terms of 1. So the question is, which one of these variables is it we want to keep? Or do we want to do it in terms of some new variable? All right? So the way we're going to do is we're going to find a relationship between these things. Okay? Between this angle and this distance and this little length guy that we're going to be adding up along here. Right? So here's what I'm going to do. I notice that this angle and this r, right, and talking about adding lengths along here, I notice I have this right triangle here. And you say with that theta, you say, maybe I can start finding some relationships with the sides of that triangle, okay, and a little trig. So that's what we're going to do. Now, I'm also, to make this a little easier to think about, instead of talking about like dl, let's like drop a coordinate axis along the wire, okay? I'm going to call it, for our purposes for this derivation, I'm going to drop what I'm going to call it the x-axis, okay? If I drop my x-axis here, let's call right here. Let's say that right here is x equals 0. By the way, this junk we're not worrying about, we're at this side of the wire. So I have some room to work here. We're going to call this spot x equals 0. Here I am, at this point, this is negative x, right? You know what I'm saying? Okay? So this length here is negative x. My position here is negative x. All right, here we go. So, what can I do with this right triangle? Well, let's try to see if we can rework some of this stuff. For example, sine theta, right, and length. So if I do it like this, wouldn't you agree that dl little lengths, that's really dx, right? So I could redefine this dl guy. I can say, hey, dl is dx, okay? So I got this triangle with these sides. You say, okay, let's try this. The question is, which variable do I want to get this in terms of? Do I want to get everything in terms of calling this dx in terms of x? Do I get it in terms of r? Do I get it in terms of theta? You say, well, first of all, this a guy, that's a freebie. We were given that value. We're trying to find it in the field that doesn't stay away, so we can use that in all our expressions. So that's good, right? But they didn't tell us r, and they didn't tell us theta. You're like, ugh. I worked through this problem earlier today with someone, and we tried saying, hey, could I get an equation in terms of x, right? And that kind of crashed and burned. It got to a point where we got an integral that we could resolve, and if we did that, we would have our answer, but the integral was really sick. What the winning move is going to be to do this in terms of theta, okay? So we're going to try to get this in terms of theta. Okay, and that's the winning move, it turns out. All right? Not saying you couldn't do it the other way, it just calc looked a little icky to me. So here we go. So we're running through this. Here's theta, right? And you say, I need to get rid of this. Let's talk about this horizontal bit. Little dl, well, let's not do that one yet. Let's talk about this r guy. Well, here. Wouldn't you agree that if I take this A, it's a side I'm allowed to use. A is a variable I was given. So let's talk about R and A and theta. Well, the relationship there is A is the opposite and R is the hypotenuse, so we're talking about sine theta. And you say, I can see from the triangle that sine theta is A over R. Which means, you say, R, the thing I'm trying to get rid of, is equal to A over sine theta. Yeah? That's the same thing as saying 1 over sine, that's called the cosecant. Am I right? I think I'm right, right? Yeah, 1 times cosecant, okay? So that's my cosecant thing. So I could, down here in my equation, where it says r, I could substitute in a times cosecant theta. If I do that, look at my equation. Again, I'm trying to find that B field strength. Right? Here, do it like this. I already pulled out that mu naught I over 4 pi. Now, down in the denominator, I'm going to square this a cosecant theta. A squared cosecant squared theta, yeah? That's what you get. Okay, now the top part, okay? That dl is really a dx, right? I'm calling it x-axis goes along the length of the wire, and the little d on the wire. So you say, okay, well, let's rephrase that now. I want to find dx and get rid of dx. Okay, this is dx or dl, right? Yeah. I want to get that in terms of theta. I want to get something in terms of d theta. So what I'm going to do here is I'm going to write a relationship for x. Now, I don't want to write it in terms of the hypotenuse, because that's the thing I don't, right? I want to write it in terms of this side, the side that I know, and this theta. So a is the opposite side, x is the adjacent side. I'm talking about tangent. You say, yeah, okay, if we do that, then you say, all right, the tangent of theta is going to be opposite over adjacent. It's going to be a over x, which means rearranging x is equal to a over tan theta. You say a over tan theta, 1 over tangent, that's called cotangent. So my x is a times the cotan of theta. Okay? Good so far? Except you say, we don't want x, we're going to want, this guy is actually dx, right? Yeah, is what that guy is, right? That is dx. So I need to get an expression for the differential here. In other words, I'm going to take the derivative, both sides. So if I do that, dx is going to be equal to, like, well, what's the derivative of a cotan theta with respect to theta? You're saying derivative of cotangent, and everyone like stops and like searches through their mind a minute, like, wait a minute, I didn't do that one too often. I work sines and cosines a lot, but not these cotangents and cosecants. Oh wait, oh that's right. The integral of cotan is negative cosecant squared. So this is going to be negative a cosecant squared theta, d theta. Right? Okay. Oh, you know what I forgot? This is an x, this is negative x. We're over on this side. Yeah? Uh-oh. Yeah, I think so. I think I want that negative. That would make this positive. I gotta think about this. I may regret that later. No, I regret nothing. All right, there we go. Okay, so that'll make this into, because it's negative here, that's going to turn this to the other side. I'll get negative. Okay, there we go. All good. Okay, so I think that's what I'm getting. Hey, what am I going to do with this? I'm going to substitute in where it says dx. Hooray. This is going to be a, and look at what happens. Look at how beautiful this is. A cosecant squared theta, yeah, d theta. Now remember, I still have that sine theta hanging around here. I'm going to put him over here. Okay, are you good with that? Look at that. You were worried when you saw cosecant squared theta in this equation, weren't you? This integral. You were like, oh my gosh, what the heck is this going to be? But look at what happens. It's awesome. Look at that. Cosecant squared theta. One of the a's cancels. And you're like, oh my gosh, this suddenly got easy. Look, that a is a constant. Let's kick it out there. U naught I over 4 pi a. What's left in the integral now? What's left here? Sine theta d theta. You're like, oh my gosh, it's like suddenly like not bad at all. You're like, I can do that integral, right? And you say, no, wait a minute. We were doing DL, right? We were saying, what if we wanted to go and find the field maybe from a wire that goes from here at negative x to somewhere over here, right? You know what I mean? Here, where I have this angle theta going there, to here, where there's some angle, some angle theta there. Let's call this one Let's call that theta 1. Let's call this angle here, different angle, theta 2. This is not meant to be symmetric, okay? It's to go from any one spot to any one spot, okay? So from this angle to that angle. So we're going to integrate from theta 1 to theta 2. That's our new bounds to match our new variable integration. I should have fixed that up here. Sorry about that. Okay. We went from dx from like here to here. Now we're doing from here to here. Okay, so this is it. Hey, can you integrate sine theta d theta? You say, sure. Remember the derivative of sine is cosine. The derivative of cosine is negative sine. And so because the derivative of cosine would be negative sine, working backwards, there's another negative side I've got to account for. So this is negative cosine theta evaluated from theta 1 to theta 2. Okay? And I still have this 4 mu naught I over 4 pi a times it, right? Okay? Now, it's just nicer to not have the negative sign. So what I'm going to do is, do you know that if you do a subtraction, I would do cosine theta 2 minus cosine theta 1, right? But if I do a subtraction then, right, times negative, right, that theta 2 minus theta 1 will become, if I multiply by negative 1, it will become just theta 1 minus theta 2. You know what I mean? In other words, if I reverse the bounds, I can get rid of that negative sign. So I'm going to do that. I'm going to reverse the bounds just to make it pretty. So from theta 1 to theta 2, it's going to be from theta 2 to theta 1, and then I can get rid of that negative sign. I know. It's just to make it look pretty, okay? So then I have this, that's it, right? Then this is multiplied by it. Mu naught I over 4 pi a, and that's my B field strength, okay? Now, we have an expression here that's actually really handy. It'll go work for any two angles, right? Going from here to here on a long straight wire. Let's solve for the special case of a wire that is very long. In other words, like an infinite wire. If it's an infinite wire, when I do this integral, I'm going to go, it looks like I'm writing from theta 2 to theta 1. So I'm going to go from here. Now wait, what's this angle going to be if I go out to infinity? That angle is going to shrink to 0. Actually, I said 0. That angle is pi. It's 180 degrees, right? 180 degrees, pi. I'm going to go from there to theta 1. If I go out to infinity this way, that angle will shrink to 0. So you say, for an infinite wire, now I have some space here on the camera, right? I can go to here. I can squeeze it in there. So if I go and I do this integral, right? That integral is going to be cosine of theta from theta 2 to theta 1. It'll be from, do you want me to use radians? Pi to 0. Is that okay? So if I do that, you see what's that going to be? Final minus initial. It'll be cosine of 0 is 1 minus cosine of pi, which is negative 1. It's just going to be 2. Okay? This is for an infinite wire. For an infinitely long wire. So that just becomes a 2. What's that going to do with this 4 in the denominator? You say I end up then with, this is what, my B was mu naught I over 4 pi a, right? Times that. So I'm going to end up with B is mu naught I, this 2 cancels the 2 down there, over 2 pi a. And that's the formula that I just kind of threw at you the other day real quick and said that's the field from a very long wire. This was the derivation for that, using the Biot Savart Law. Yeah, what do you think? Kind of long. Here's what I'm going to tell you. You know that I've taught this course for over 20 years, right? And that generally just about any topic from the course, you want to say, hey, Mr. C, can you teach me about blank? And I'll be like, oh, okay, here's how it works. Do-do-do-do-do. There's just a couple derivations and things that are tricky enough that I need to go back and look at and refresh my memory on before I try them. This is one of them. Okay? So if this seems a little awkward, like hopefully it made sense as I went through it. But when you first saw it, you're like, you know, you see this thing, you're like, how do I apply that? Okay? This is really kind of icky with straight wires. Okay? This derivation. It's kind of long and awkward. All right? The good news is there's another way of calculating magnetic field strength. It's called Ampere's law. And it does the straight wire derivation that we just did here, that did all this. It does it in like 4 lines. Choop, 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 done. Mu naught I over 2 pi I. Done. Okay, so I'm going to show you Ampere's law in the next video. But first, I want to point out what we can do with this. First, this one, trying to use this expression for a straight wire, what it lets us do, it lets us do a wire that's not infinite. We can just go from this angle to this angle, whatever the angles are for this wire that's that long. This is how you handle a non-infinite straight wire. You're going to use Biot Savart Law. The second thing, and this is where the Biot Savart Law shines, is this was really awkward because of these angles and stuff. I'm going to erase this, and I'm going to do Biot Savart Law, but I'm going to do it for a case where it's awesome. Here we go. This time, we're going to do the Biot Savart Law. Not for current down a straight wire, but current through a wire that's bent in an arc. Okay? So check this out. Say I have a wire that goes along like this. And then, here's like a semicircle. Okay? So say I have current flowing down this wire, right? And say that wire has a radius, it's like a circle, it bends like a circle with a radius we'll call big R. And I want to know, right here, what's the field strength at the center of that arc? Okay, center of that semicircle, right? So right there, now in this case, if the field's going down the wire that way, as it comes up here, doesn't it make sense the field be going into the board, into the board, into the board? So my magnetic field here will actually be X into the board. You know what I'm saying? Going away from me. It's the tail fletchings of the vector going into the board. Okay, into the page. So here we go. Let's find that B there. Okay? So we're going to find B at center of a semicircular arc of current. With radius big R. Sorry, I should go in there. Of current I. All right, here we go. So good enough. So here we go. First thing, we're using the Biot Savart Law here. Let me, I'm going to write it over fresh. So you say, hey, dB is mu naught I dl cross r hat over 4 pi r squared. Okay. Now, first thing, we say that cross r hat, remember that means there's going to be a sine theta there, where theta is the angle between dl and r hat. So here we go. You ready? An r vector, that's a vector goes towards the point, from the little bit of current to the point where you're measuring. Watch this. Look at this little bit of wire here. It's going that way. Which way does the r vector go to this? Oh, it's going that way. Hey, look, the dl and the r vector, they're going the same direction. What's that going to be? Sine of 0 is 0. All of this wire here adds nothing to the field strength here. Same thing with this wire here. Sine of 180 is 0, right? It's just the wire in the arc that matters. Right? So that's cool. Wires don't make any magnetic field along their length, which is important because if they did, the current going through would make a field that would affect the current that's making the field. It'd be a mess up. But anyway, we're getting here. So we're doing this. Wires tugging themselves places. That doesn't make sense. So here we go. So here's this, yeah? So the field here is going to depend on the current in this part. So I'm going to look at this, and I would take this guy, and I would split it up. All these little DLs, you know what I mean? DL, DL, DL. Let's add up the field contributions from each little DL going around here. So let's just look at one of them chosen at random here for right now. Let's figure out what's going to happen here. What's going to happen? Well, first of all, mu naught's a constant. Let's kick out all our constants out because we're going to integrate, yeah? Kick out all our constants. What have I got? Well, mu naught's a constant. The current flowing all through here is a constant. I've got that DL, right? Cross r hat. Well, r hat is just 1. It's a unit vector. Its value is 1. The sine theta, that's the angle between DL and its r vector going to the point we're measuring. Well, what's that angle? Well, for a circle, that's just 90 degrees, isn't it? So that's just going to be, in this case, sine of 90, which is just 1. Okay? So if I'm looking at this little guy here, his r vector for this little guy here, I'll just make that one in particular, his r vector is going like this, yeah? That's the way his r vector goes. You say, hey, they're at a right angle. That's a 90 degree. Chuk, chuk. And so sine 90, just 1. So that goes away. That sine theta goes away. The r hat's just 1. This whole cross product's resolved. I didn't make this clear here, I apologize. The first thing I resolve when I solve the Biot Savart Law problem is I take care of that cross product. That's the first thing I do. I get that cross r hat out of there, right, and rearrange it. R is just 1, I'm just getting a sine theta, okay? I need that in the formula to remind myself to do the right-hand rule to figure out the direction of B, but I get rid of it for calculating. Okay, I resolve it right away. I figure out what that sine theta is and take care of that, what that is. So in this case, that's just 1. So you're like, oh, it's just dl, right? Okay, that stays in the integral. Anything else coming out? 4 pi. Anything else coming out of the integral? What's that r? Oh, r is just the distance. Well, wait a minute. It's the same distance for all this. It's just big R. That's it. That's what I get. All that's left in the integral is just that little bit of length. What happens if I add up all these little bits of length here? That's just the length of that arc, which in this case, that's half a circle. So the length of that arc is what? Half of 2 pi r. It's just pi r. So you're like, oh, this is mu naught I over 4 pi r squared times, not 2 pi r, half a circle, pi r. What's that going to be? Pi's going to cancel. One of the r's is going to cancel. It's just mu naught I over 4r. That's the B field for this case, for a semicircle. Neat, huh? It actually comes out a nice, simple little equation like that. And it's not that hard to get once you recognize which things are constant and pull them out and take the cross product first. Okay, hey, what if instead of having a semicircle, what if I had my wire comes in and it goes around in a complete loop like this and then maybe goes out? Okay? What if I had a complete loop of radius r? I want to find the B field at the middle. Right? Again, if my current was coming in this way and going around this way and then coming back around this way, right? You say, it would make field going into the page in the middle. My field would go in here. Well, it's going to be the same derivation, right? Except when I go, and it's still mu naught, I are constants. It's still going to be for each little bit of the length, the r vector is going to be at a right angle to it. So it's going to be sine of 90, which is 1. It all pops out, right? Except instead of pi r, I'm going all the way around the circle, so that would be 2 pi r. So for this one, I'll have B is mu naught I over, it was 4 pi r squared times, and now it's going to be times 2 pi r. So the 2 will cancel part of the 4. Pi's cancel. I get this. So this is for a complete loop. Mu naught I over 2r is the strength of the field at the center of that loop. What would happen if I ran a coil? And so I have, it loops and it loops around again, it loops around again. What if it loops around n times? I'll just multiply this by n, won't I? To get the field strength at the center. Okay, hey, what do you think? So Biot Savart Law, it's not bad for curves, right? For like arcs of circles, and find the field right there at the center. I know, special case, anywhere else would be a problem. But you say, but finding right there, it's actually really quick and slick to do. Okay, that's something we can do. So, if I'm trying to find the field strength for a wire that is part of a circle, like an arc or something, like maybe the wire comes in and goes off at an angle, you'll see it in a homework problem. Then Biot Savart Law is the way to go. If I have a straight wire segment that's non-infinite, sad to say, you got to do this junk and go figure out the angles at the two ends of the wire, right? And go from that angle to that angle. If it's an infinite wire, you could do this to get it, but Ampere's law will be a quicker, easier way of doing it. So, hey, that's it. This is what I want to say about the Biot Savart Law. There's problems in, of course, the unit packet that you want to take a look at. But, yeah, that's the intro to it. To my mind, this is the most alien to me and scary to me looking equation, I think, in the unit, or in the, I was going to say in the course. I don't know how you feel about Gauss's law. Hopefully now Gauss's law is like an old friend. But this one you're like, hey, yeah, that's a little weird with it in terms of it as a differential instead of like B equals, dB equals. You're like, why am I writing it like this with a cross product and a unit vector? You're like, what? but hopefully it makes sense where it comes from and how to use it.